Hey guys, welcome to Digital Srini channel on YouTube, and as usual I request you to please subscribe to this channel if you haven't already done so, because seeing the number of subscribers is a form of motivation for me to create more such content. And if you're feeling extra generous, go ahead and hit the thanks button to contribute whatever you feel like. Now, for the last 10 videos, I believe I have been talking about generative adversarial networks. We looked at various incarnations of GANs, or various ways we can actually apply this GAN architecture for various applications. And here we go. I came back with another such example. This is called semi-supervised learning with GANs. And what does semi-supervised mean? Well, a full supervised or a supervised based learning means you have your data and corresponding labels, and this can be images and what class these images belong to, or these can be images and masks for semantic segmentation. So, but this is all supervised. Unsupervised is you just have a bunch of data and you want to classify that or segment that or whatever the task is. So that is unsupervised, and semi-supervised falls somewhere in between, meaning you have some labeled and a lot of unlabeled data. So let's first understand what semi-supervised learning is, and then we'll get into the GAN part of it and what is the basic benefit of this semi-supervised part of the GAN. It's definitely not the generator like we normally use in any other GAN, so that's just a hint. So in semi-supervised, like I already mentioned, you have both the labeled data and unlabeled data, but you have very few labeled and a lot of unlabeled. So think of a scenario where you have like 10,000 images that you would like to use for training for semantic segmentation. Okay, on day 1 you got done with 5 images, day 2 5 more images, you got a bit more efficient, on day 3 you got 10, day 4 you got 10 more. So in a week you got like 100 images labeled, and then you kind of give up. There is no way you can actually annotate all of your 10,000 images, and maybe those 10 images, 20 images that you labeled or annotated, can you effectively use that to get good classification or segmentation, whatever the task is? So that's exactly where semi-supervised learning fits in. Maybe there is hope with semi-supervised learning if you have limited amount of training data, but you have a lot more data that is unlabeled. So now, first of all, the primary use of this is, like I just mentioned, I keep mentioning about using the labeling data, small amount of labeled data, to create a classifier. Let's just call it a classifier that is much better classifier than just using a classifier that gets trained on a small amount of labeled data. What do I mean by that? So let's look at a simple example of Amnish dataset. It has 50,000, I believe, or 60,000 training images. And you use all those training images and you get, I don't know, 95% accuracy. We feel good. We are great. What if I only give you 100 images? 10 images for each class in the Amnish, right? 10 images that represent letter 0, 10 images for 1, and so on. What kind of accuracy can you actually get on your entire testing data set? So let's jump into the code to get a quick understanding of that, and then I'll come back to this to finish this presentation off. And stay tuned for the next video where we'll actually implement this entire SGAN or semi-supervised GAN in Keras, but I'll show you snippets of code later on so you get a good understanding of what to, how this actually works. So here I'm just showing you a quick Amnish classification. Most of you probably started off with this, right? When we started learning about deep learning, this is an exercise that we typically do. So this is no different than that, except I'm only using I believe in this case 100 images, like I just mentioned. So let's go ahead and import the libraries. Again, I'm no point in explaining any of this. You should be knowing this. Otherwise, go back to the basics and learn more about basic deep learning. So these are all the layers that we plan on using to build our model. The next function I defined here, this basically gets images or fetches images from our Amnish dataset. Remember, I am using Amnish right there to load the data. So loading the data, it gives us train X, train Y, and test X and test Y, right? So these are the 4 things that it gives us. And I'm just taking my training data, expanding the dimensions, converting that to float 32, divide by 255, like we normalize all the pixel values to between 0 to 1. And this function just returns my processed X and then the labels. So that's what this function does. And then this function here, it actually gives me 100 images, 10 images per class, all picked randomly from my Amnish dataset. So basically, it's just looking at 10 images per class, and we check, okay, what is the class label? And from those, go ahead and generate a random, numbers right there, and get 10 images number per class, right? So get that many images from that specific class. So all it's doing is just returning 100 images randomly picked, making sure we have a good balance between each class, meaning I'm getting 10 images per class. So let's go ahead and run that function. And now let's get our data set, which is basically, I'm calling my get images ready function right there. So I should have my data set with 2 NumPy arrays. One, let's open that one with 60,000 images. These are the training images, each 28 by 28 by 1. And the other one is my labels, right? So what does that mean? What is that first one? It's basically representing letter 5. Okay, I'm sure you know what Amnish is. So let's move on and get a subset of images. We don't want all those 60,000. We just want 100. That's the whole point of this exercise. So let's just get our X and Y. And if you look up here, I have my X 100 images, my Y 100 labels, and they're all sorted from 0 to 9. And if you are curious, we can go ahead and plot a few random ones. So there you go. So that looks like letter 3. The next one looks like letter 9. Next one looks like letter 9, letter 8, and so on. I don't know. That could be 4 or 9, depending on, yeah, this is definitely 4. So we know that, okay, we have our data. So let's split our data into training and testing. In fact, let us get 120 images and assign 20%. So that way, let's go ahead and run that one more time. Sorry about that. Let's get 120 images. I want about 100 images as for our training, even after assigning or testing data. So let's go ahead and do that. And now when I do X train, Y train, now I should have 96 images. That's not bad. 96 images for training and 24 images for testing. Okay, so far so good. Obviously, most of you should know this. Again, these are all the basics of deep learning. And I assume you know this because you're watching a video about generative adversarial networks, and without knowing the basics, you're wasting your time if you're watching this video. Okay, now let's define a model. Again, you can define different types of models. I just defined something that I had in my files from 2-3 years ago when I did this for the first time. So basically 3 convolution layers, 32, 64, and 128 of these features, and then I flatten it out and I drop. I added the dropout for in this specific case because we are dealing with a limited amount of data. I don't want to overfit. And you can try dropout somewhere in between, but again, this is where you can just go ahead and experiment. Now, one other thing, you probably have noticed that I did not convert my labels into categorical for multi-class classification. Obviously, you convert your labels to categorical. I just wanted to keep things very simple and straightforward. So I am using sparse categorical cross entropy loss, which doesn't require us to convert this into categorical or one-hot encoded. So it does work with our integer encoded labels, just like how it would work with your random forest or support vector machines. We don't have to convert that into one-hot. That's the only note I would like to make. Everything else should probably make sense. So let's go ahead and print the model summary. This is very simple. So 3 convolution layers, that brings your images from 28 by 28 to 13, 7, 4, all the way down to 10, right? So these 10 are our 10 classes. So let's go ahead and fit this. This should be pretty fast. So let's go ahead and run this. So all I'm doing is a batch size of 64 with and running 100 epochs. And let's see what type of accuracy we actually get. Okay. We probably get pretty good accuracy on the training data set, but then if you look at the validation data set, I'm getting like 79% on the 24 validation images that we have. In fact, if I apply this to my 10,000 validation images, the accuracy will be much lower. So this is an overfitting problem. Again, you can play with this, but let's work with this data set, with this model. So let me go ahead and save this model. And first of all, if you are curious about how the training curves look like. Let's go ahead and plot them. You see how it kind of saturated at about 79%. That is a limitation from the model and also from limited data. So I'm pretty confident if you add, let's say instead of 100 images or 96 images, if you go to 200, 300, 400, this is a good exercise if you just started off with deep learning. Go ahead and increase the number of images and see how this accuracy gets affected or influenced by that. So now let's go down and go ahead and load the model we just saved. I'm just loading it right here. And then let's load the data. This time, instead of training, let's load the testing data set, because testing data is 10,000 images, right? So if I go to test X, it's 10,000 images. Why am I doing this? Because the model I just saved, I want to see what the accuracy is on the data it never saw, a bulk of the data that it never saw, right? So let's go ahead and get this data ready, convert that into float 32, all the steps that we have done during the training process, divide by 255. And now let's go ahead and do model.evaluate. And what is the accuracy? This is the moment of truth. So our accuracy, that's not bad. 79% using only 100 images. That is pretty good. Now, can we improve this to above 90%? Can we get like 91, 92, 93, even above 95%? We will see with using only these labeled images, 100 labeled images. That is the key point that I'm trying to make here as part of this semi-supervised GAN training, because I want to make sure you understand exactly when the semi-supervised GAN is going to be used. So just for the sake of completeness, let's go ahead and print the confusion matrix. So as you can see, yeah, there are a lot of misclassifications right here. So we'll look at exactly the same thing in our next video when we go through this semi-supervised GAN training on the same data set and then compare apples to apples here, compare against this accuracy and compare against this confusion matrix. Now let me get back to the presentation part to make sure you understand every aspect of this semi-supervised GAN. Yeah, that's the whole point. I don't want to do the Keras part in this video, which makes it an hour-long or 1.5 hour-long video. That's not the right way of learning. That's why I'm breaking this into two. So I hope you appreciate that part. So let's get back to our presentation. And this is where we stopped, so let's continue. So what is semi-supervised GAN? Now that you have an idea of what the limitation of regular convolutional networks or regular networks with limited amount of data, let's understand semi-supervised GAN. So in a regular GAN, in a regular generative adversarial network, the discriminator is trained in an unsupervised manner, right? So the discriminator looks at this data and it just classifies that as either fake or real. Because generator is giving it fake images and we are also supplying real images, and we label the real images as 1 and we label the fake images as 0. So when I say unsupervised manner here, I'm not talking about labeling the real as 1 and fake as 0. I'm talking about is this a cat or a dog or a monkey or what is it? We're not supplying those labels at all. So in a regular GAN, it's just unsupervised discriminator. That's it. Is it real or fake? In SGAN, or semi-supervised GAN, in addition to this unsupervised, we are also doing this unsupervised. The discriminator also gets trained on supervised. So we supply the class labels in addition to supplying is it real or fake. So this is the key difference here. So the discriminator, in this case, the supervised discriminator, is nothing but a multi-class classifier in a GAN. Things will make sense if they don't yet. And there are two modes. Think of this as having two modes. The discriminator has two modes. One is unsupervised, one is supervised. And in the unsupervised mode, it learns the features. Again, what is unsupervised mode? This is like a regular GAN. It doesn't know what the labels are. So think of this as transfer learning. What do you do with transfer learning? You have a network architecture and you chop it off at the classifier, right? Take a VGG16, you take that. And why is that useful? Because it is a feature generator, because it got trained on ImageNet, for example, to generate a lot, to understand the features. Think of our unsupervised mode as exactly the same type of thing. It is being learned during the training process, and it learns the features. And then in regular GAN, we focus on training the generator and discard the discriminator, right? The discriminator is there only to make the generator better at creating fake images in regular GAN. In this case, in our SGAN, we do not care about the generator because the generator is there to make our discriminator, the supervised discriminator, a better classifier. So we do not care about generator. In fact, you can keep it if you want, but we usually throw that out. And we only keep the supervised classifier, which is the discriminator right there. Because the whole point of semi-supervised GAN is not to come up with a generator that gives you great images, but to come up with a classifier that works great in classifying your data. But that classifier got trained only on the limited amount of data that you got. So that's the whole point of semi-supervised GAN. Okay, and SGAN approach achieves better accuracy for limited labeled data compared to CNNs. This is not a statement I'm actually making, out of nowhere. Go to this paper called Semi-Supervised Learning with GANs, and they actually published, for example, if you look down here, compared to a CNN approach versus SGAN approach, with only 25 images. In CNN, you got 75, and then here you got 80%. And in fact, with 100 images, on Amnish dataset, we saw 79% right now, right? Maybe I can play with the models a little bit to get better accuracy. And here they got 92.8%. That's better. But as this data size increases, both are giving similar results. So following this approach doesn't mean you're not doing the best job. In fact, you're doing the best job even with limited amount of data or a lot of data. But if I have lots and lots of data, I would directly jump to CNN anyway, because remember, GAN training is slower compared to regular CNN training, okay? Because you're training 3 models here. Now, discriminator supervised, discriminator unsupervised, and generator. Okay, now in summary, what do we learn here? The discriminator has 3 different inputs in our GAN. Real images with labels, real images without labels, and fake images. Where are they coming from? They're coming from the generator, and these 2 are like our regular GAN. This is like our multiclass convolutional neural network. Okay, just for those of you who understand this in a visual way, this is something I showed you a few tutorials ago where we looked at GANs, generative adversarial neural networks. So where you can see the generator, the input to the generator is a latent vector, or random noise if you want to call that, and taking that, this gets reshaped, and then it creates reshaped into a size of whatever our fake image is, and that fake image goes into our discriminator. Also, 50% of the time, real images go into the discriminator, and the discriminator is trained to discriminate between real and fake, and when these 2 go in, a extra label also goes in that says, hey, this is a real image, the label is 1. This is a fake image, the label is 0, and the discriminator gets trained. Eventually, it gets better by improving on the discriminator loss, and the generator also gets better because we are training it in this combined model. Now, if I convert that into a semi-supervised GAN, you can see the structure is very similar, except in addition to fake images to the discriminator and unlabeled real images, we also send labeled a little bit, a few of these labeled real images to the discriminator. And now comes the part. Think of this discriminator as just a feature extractor. This is not a binary classifier. Here, this discriminator is a binary classifier to classify it as real or fake. Here, I'm using discriminator only as a feature extractor, the first part of the discriminator, and then I extend the functionality of this discriminator by adding a classifier to make it binary or make it multiclass. So I have 2 different models here, one unsupervised, one is supervised. I hope this makes sense. And what does the unsupervised does? It's just a binary classifier, real or fake. And the supervised is just a multiclass classifier. It's going to classify this as either 0, 1, 2, 3, 4, 5, 6, or something, right? So this is a multiclass classifier, which means you can, as you can imagine, here we are going to use softmax activation function. So we'll look at the code in a minute. Now, moving forward, now I am showing you a few excerpts from a couple of papers, publications, which gives you a bit more information. First of all, this is a great publication to go through, Semi-supervised learning with generative adversarial networks, and the abstract itself summarizes the whole paper. This is, I think, only 2 or 3 pages long. That's it. And they're talking about extending GAN to semi-supervised context. How are they doing that? By forcing the discriminator to output class labels. We just talked about it. And they train a generative model and a discriminator on a data sets with belonging to one of the n classes. Think of, again, Amnish. You have 10 classes, so that's what n stands for. And during the training time, the discriminator is made to predict 11 classes. 10 classes are the real classes, and the 11th class is it real or fake? Okay, the 11th class is basically fake. If it has a class label, it's real. If not, then this is the fake right there. Okay, and also another paper that can be very useful is improved techniques for training GAN. And the reason I'm flashing this screen here is these guys actually talk about a nice technique to speed up or to come up with this discriminator architecture. And one of those, again, you can go to, I don't want to intimidate with all of that stuff, but I just want to show you one quick thing here. So the way they're talking about implementing that is via using stacked supervised and unsupervised discriminators. Instead of having one discriminator for the unsupervised, one for the supervised, what if you can actually stack them together? Meaning up to some point they're pretty much the same, and then this is how you would handle that, right? So the supervised loss becomes the standard supervised loss function of our original classifier with k classes, right? So this is our this is our supervised because we have k number of classes. So first you define a supervised model, and then to convert that into unsupervised, all you need to do is just add this layer. I'll explain that in a second again. So all you need to do is just add this layer. Obviously we need to remove the softmax layer because that converts your nodes into some sort of a classification, right? So one of our 10 classifiers. So let's remove the softmax, output of the softmax, remove that from our supervised or multi-class classifier, and then just add this layer. So I hope I haven't lost many of you already, but let's look at the summary or the essence of that. So instead of defining 2 different models for the discriminator, a good or efficient way to implement would be to reuse the output layers of the model, like I just mentioned, to feed in as input to the another model. So according to this paper I just showed you, the supervised model is first created with k output classes, right? And what do we use for that? We use softmax activation. Think of the supervised model as the one that I just showed you for Amnish. A bunch of convolution layers and then just 10 outputs. That's it. And the unsupervised, it takes the output of the supervised model, obviously before the softmax activation. Yeah, we don't want the activation right there. And it calculates a normalized sum of the exponential outputs, which is nothing but that equation I just showed you, this one. Yeah, it just calculates. What does it calculate? Normalized sum of exponential output. Exponential of the output, sum it, and normalize it. Zx over Zx plus 1. Okay, so this is what we need to define. And remember, in our binary classifier, is it fake or real? We have a sigmoid activation function in our generative adversarial network, typical standard GAN. Here we do not need the sigmoid activation because this itself is like an activation. This is normalized. Why do you use sigmoid? To bring your output to between 0 and 1 and convert that into some sort of a probability, right? So it reflects some sort of a probability. Here you don't have to do that because this is already normalized. So no point in adding a sigmoid activation. That's another point here. Now let's look at a few lines of code just to get a quick understanding of, okay, we went through all that, but actually when it comes to implementation, it's not that tricky. It's not that difficult, I should say. So what are we going to do? Standard implementation of let's only look at generator right now. There is no difference in generator. It looks exactly the same. So how do we start a generator? It takes in a latent vector, like I usually use the size of 100, and you convert that, or you increase that into, in this example, 256 7x7 nodes, and you progressively add your conv2d transpose and activation layers to bring it to a output of whatever the image that you are trying to create. So in this example, if you follow this output would be 28 by 28 by 1, which is exactly what we want because that's our Amnish size, right? Data set size. So generator, exactly like your regular GAN. Discriminator, this is where we have to focus a little bit. So let's just start by looking at the base of the discriminator. So first of all, we are going to use the stack discriminator approach, like we just discussed, which means we have to add that extra layer. So we'll save that for now. And the standard it's mostly a standard implementation of discriminator, by the way. The only difference is now we have unsupervised and supervised towards the end. So what does the standard implementation do? The whole point of discriminator is takes an image and then generate the feature, and then you have a classifier, in a binary classifier or a multiclass classifier. So we define this, and the image size, input image size for Amnish is 28 by 28 by 1, and also it takes in the number of classes as 10, right? So in this case, the reason why I'm including number of classes is I would like to output a dense layer with that many classes as the last layer right here. So it's going through conv2d. Remember, this looks exactly the same as the model I showed you in my Spider IDE for my Amnish, because I want to use exactly the same model. We had a conv layer with 32, 64, 128. I flattened it. I added a dropout of 40%, and then this is basically the class, the model I showed you a few minutes ago. So this is my discriminator or feature extractor as part of discriminator. After this, now comes supervised discriminator. What is supervised? This is the classifier we just defined in our Spider IDE. What did we use? We used an activation of softmax right there. And then we used sparse categorical cross entropy because, like I said, I don't feel like converting my Y values to categorical. So I'm going to use sparse categorical cross entropy that can work with integer encoded labels. And I'm using Atom Optimizer. Everything exactly the same as what I just showed you. Rewind the video, go ahead and look at that model and look at this model. This is exactly identical. Well, mostly identical, except here I'm using leaky ReLU instead of ReLU. So this is my supervised discriminator, and hopefully everything makes sense for you. So I defined a discriminator, base discriminator, which I'm calling right here. And to that, I added softmax activation and finally compiled the model. How do you do the unsupervised part? This is where this custom activation function comes into picture. So first, let's go ahead and define the custom activation. It takes in an input of x, okay? And then what is our zx right here? Zx is basically the sum, right? This summation. In Keras backend, there you can import this sum and exponential of our x. That's it. So you have summation e to the power of x, and I take that zx and divide by zx plus 1. So this custom activation takes in x as input and returns a dx right there. Now I just need to add this, and it's very easy in Keras. How do you add a custom function as a layer in your model? You just need the lambda layer. So this lambda is available as part of your Keras. So go ahead and add that. So here, my unsupervised discriminator is nothing but this part that extracts the features and gives you 10 classes, right? And then take that discriminator and add a lambda layer on top of it. And then because this is binary, we are going to use binary cross entropy, and the optimizer is my Atom Optimizer. This is it. This is my unsupervised. And how do you define a GAN model? Exactly same as your regular GAN. So this is a composite GAN model where your generator gets trained via the composite GAN. What does that mean? In our regular GAN, when we put a composite GAN, we fix our discriminator to be untrainable or non-trainable, right? That's exactly what we are doing. So in this GAN, the only inputs are your generator and your discriminator of unsupervised kind, right? So this is the binary discriminator. Exactly same as your regular GAN. And we are going to set this as non-trainable, and everything else is pretty much the same. You're generating, you're training, compiling using your binary cross entropy, and pretty much exactly the same as your regular GAN. So the only difference lies in your discriminator right there. And also, how do we train this? because we have to train this on both supervised and unsupervised discriminators. So if you look at that, SGAN training process again is very similar to GAN training. Like I said, we need to update the weights of the supervised model. So how do we do that? So all of this is basically defining your number of steps and all that stuff, but just look at the meat of it right here. So for each of these steps that we're going through, first of all, we are going to get real samples, okay, along with the labels. So we are going to get real samples along with the labels. So we have our X as a real image. Let's say the image is like corresponding to the number 5, and the label here is 5. That's what I mean right there. So this function, we'll see, look at this in the next video, is giving me a real image and the corresponding label. And then my supervised discriminator is going to be trained using train on batch on these two, on this data. So you get your loss and you get your accuracy right there, right? So for this data. So that's pretty much it. So this is how we are going to train the supervised discriminator. But when you go down, we have to train our unsupervised, which is our regular discriminator. How do we train our unsupervised? You know this, right? We first give it a bunch of real images with a label of 1 and train it. And then we train it on fake images with a label of 0. And then we train our generator via the GAN. That's exactly the steps we're following here. So first we need to generate real samples. So you get some, which is basically get real images. Okay, and then this Y real is 1 because these are real images. Don't confuse this with Y supervised real. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is actual real labels. So here we don't need real labels. We just need the label equals to 1. So real image, real label, which is 1. And then you train your unsupervised model. And then we need fake image and fake label, which is 0. So how do you get fake image? Well, you actually use a generator, right? Your generator to generate a fake image. And then that's what this function does. It goes to the generative, it uses the generator with the latent dimensions, and then it actually gets you a fake image, and the fake label equals to 0. And now we train the unsupervised discriminator on that data. So at this point, the discriminator is trained. Now we get to the generator. How do we generate the generator? Via the combined model that I just showed you, where the discriminator is fixed and only the generator is trained. So this discriminator unsupervised is fixed because we already trained it. And now the generator gets trained on our generated, on our data right there. On our obviously, we're going to generate latent points, and that's what we're going to use as input here. So again, this is very similar to our regular GAN. I hope this process makes sense. The only point I would like to make here is this approach of SGAN is not to train a generator to give so that you can use that to generate like fake images or fake data later. But the process here is followed to create a classifier that works, or that we can train effectively using limited amount of training data. So in the next video, let's put all of this to practice and train our discriminator, the supervised discriminator. Of course, we're going to train everything. We're going to save the supervised discriminator and look at its efficiency, or look at its accuracy, I should say, compared to our regular convolutional neural network approach. So please stay tuned, guys, and hit the like button if you really like this video. Again, that's a great way of providing me the feedback about what type of content you're finding useful, so I can put more energy into developing those, that specific content. Thank you. Let's meet again in the next video.